Hello, my name is Elizabeth Nagley and I am a director with TNTP. In session 3, we are going to explore the topic of strong science instruction. In this session, we will apply our learnings from session 2 to consider strong science instruction. When you leave the session, you should have the tools that you need to help you think critically about your vision for strong science instruction and how students are preparing for future STEM career possibilities. To get the most out of this training, we ask that you have first completed Session 1 on the opportunity myth and Session 2 on grade-appropriate assignments in science. As with Session 2, we encourage all science teachers or leaders who support science teachers to engage in this session. This session is designed to take approximately 1 hour to complete. Over the course of this session, I'll prompt you to pause the video to engage with resources through written reflection and practice. I'll give you cues for approximately how much time to spend on each activity. Though feel free to move at your own pace and slow down to take as much time as you need to complete the activity before moving on. As you saw in previous sessions, in today's session there will be opportunities for you to engage with the content. When you see this orange folder symbol, you'll want to open the STEM.LD resource folder and access a document from that folder. When you see the light bulb symbol, you will pause the video for reflection. When you see the green pencil symbol, you will pause the video to engage in some practice. At the very end of this session, there will be a short survey that will record your attendance and completion of this session. For this session, you will need to open the Google Drive folder for Science Session 3. Pause the video now to open this folder. To open this folder, you can type the web address into a browser or use the QR code shown on the slide. Resume this video once you have opened this folder. Before we go on further, let's take a moment to reground ourselves and what we are seeking to achieve through STEM instruction in our schools. Let's watch this video from Neil deGrasse Tyson to help us understand the important role that science education plays in our society. As you watch this video, consider the implications that this has on science instruction in our classrooms.
When I think of science, I think of a truly human activity, something fundamental to our DNA, something that drives curiosity. When you're a kid, you're born a scientist. What does a scientist do? We look up and say, I wonder what that is. Let me go find out. Let me poke it. Let me turn it around. This is what kids do. Kids that can barely walk, what are they doing? They're turning over rocks. They're plucking petals off a rose. They're exploring their environment through experimentation. That's what we do as human beings. So what do? We prevent that. We prevent these depths of curiosity from revealing themselves, even within our own residences. You know, we spend a year teaching our kids to walk and talk, and the rest of their lives tell them to shut up and sit down. What kind of environment is that? The goal here is not to make everybody a scientist. That's not the goal. What a boring world that would be. You want artists, you want musicians, you want novelists, poets. You want the rest of this. What matters is whether they're scientifically literate and maintain that literacy and that curiosity throughout their lives, no matter what becomes their profession. People think science literacy is being able to recite facts, and it's not that. It's a part of it, but it's not the main part of it. The main part is, how do you look at the world? What does the world look like through your lens? If you're scientifically literate, the world looks very different to you. It's not just a lot of mysterious things happening. There's a lot we understand out there, and that understanding empowers you to first not be taken advantage of by others who do understand it. And second, there are issues that confront society that have science as their foundation. You can't look at science and math as some separate subject. It's fundamental to what it is to be alive because it's all around us. And it influences your health, your safety, how you're going to have to vote, what issues are before you politically. If you're not scientifically literate, it's in a way you are disenfranchising yourself from the democratic process, and you don't even know it.
In this video, you heard that our goal is not to make everyone a scientist, but our goal is to make everyone scientifically literate, which doesn't just mean that you're able to cite scientific facts, but that you are able to critically look at the world through your own lens. And knowing that scientific literacy is the goal has implications on the way in which we teach science in our classrooms. To create scientifically literate communities, students need to have access to all of these 4 key resources in their STEM classrooms. Strong instruction is one important component of this framework. In this session, we will explore the question, what does strong instruction look like in a science classroom? Here are the goals for this session. We will begin by internalizing a vision for strong instruction using TNTP's Science Walkthrough tool. We will analyze instructional practices in science that engage students and give them ownership of their learning. And finally, we will reflect and make connections to the larger STEM.LD work. TNTP's Instructional Walkthrough tool can help us understand if students have access to strong instruction. We can also use this tool as a foundation for our own vision of what strong instruction looks like in practice. You can access this walkthrough tool in your STEM.LD resource folder. Pause the video to locate and open this document entitled TNTP Science Instructional Walkthrough Protocol. After you've opened the document, take 3 minutes to review the tool and make notes on how it is organized. Jot down any questions you hope to have answered by the end of the session today. After you have reviewed the tool, resume the video. The goal today is not that you learn how to rate instruction using this tool, but rather we're going to focus in on the indicators that help to illustrate for us the components of strong science instruction. As you saw in the walkthrough tool, we begin by looking at whether there is a culture of learning in the classroom, by which we mean, are students engaged in the work of the lesson from start to finish? We look at this first because we know that if students are not mostly on task and focused on the work of the lesson, then the teacher will likely need to address classroom culture before or while addressing the quality of the content or thinking that's happening in the classroom. For today's session, all the examples we will see are strong examples of classroom culture. For that reason, we won't spend additional time here focused on this part of the tool. After culture of learning, we consider high-quality scientific content. We want to see if students are working with science content that reflects the key instructional shifts that are articulated by the Tennessee Science Standards. You can see the 2 indicators here are similar to the indicators that we considered when looking at grade-appropriate assignments. That is because we know that if students aren't working toward rigorous grade-level standards, the rest of what is happening doesn't matter. The standards build intentionally within and across grade levels to prepare students for college and career, and therefore, this must be considered first in regard to excellent science instruction. So in considering high-quality content, we ask ourselves if we see evidence of 2 things. The first is that instruction is focused on making sense of a phenomenon and/or designing solutions to a problem. In our last session, we defined a phenomenon as an observable event that occurs in the universe that we can use our scientific knowledge to explain or predict. And we discussed the importance of an anchoring phenomenon in science instruction. The second indicator focuses on whether or not the lesson develops disciplinary core ideas, science and engineering practices, and cross-cutting concepts. Let's start by analyzing a classroom. The lesson we will analyze today comes from an 8th grade classroom. Pause the video here to read the standard associated with this video. After you've read the standard, resume the video. For this lesson, students are focused on 8.ESS2.4, which explores plate tectonics. In this standard, students are expected to gather and evaluate evidence that energy from the Earth's interior drives convection currents within the asthenosphere, which creates changes within the lithosphere, including plate movements, plate boundaries, and seafloor spreading. In this video that we are about to watch, we will see a teacher leading a discussion with her students. Prior to this video, students have watched a video themselves of an earthquake occurring on Mount Everest, and they've also read a news report about this event. Students recorded their ideas in a notice and wonder chart and then discussed them in small groups. Now, the teacher is bringing them back together to share out their ideas as a whole class. As you watch this video, consider whether these students have access to high-quality content as described in the tool. Jot down notes as you watch.
Did you guys know this? I found that it shrank 2 feet in that it shrank 2 feet in 1934.
No, it says here, however, the data show that the earthquake moved the mountain doesn't say that
it moved 2 feet
oh yeah.
in 1969.
Well, it didn't change height, but it did move directly.
Well, like it shrunk by 63 centimeters. And that's kind of a lot.
After gathering data from sensors, scientists determined that Mount Everest did not change height due to the massive 7.8 magnitude earthquake and will continue to grow at its normal rate.
Yes, but it also says in the last major earthquake near Mount Everest in 1934, the mountain shrunk by 63 centimeters, which is almost 2 feet. So that's what I wrote down in my notes.
Oh well, it did shrink 2 feet, but it wasn't caused by the earthquake.
In the last major earthquake near Mount Everest, it shrunk though.
They're saying scientists were curious if the earthquake had caused this. Then later they said because when they collected data, they said it did not change height due to the massive 7.8 magnitude earthquake.
Yes, but I'm writing in the notice because I noticed that in 1934 it shrunk.
Oh yeah, so you're gonna see like why it shrunk?
Yeah.
I see lots of great questions, lots of people jotting down what the article gave them.
And I also see that Mount Everest is
So if it's not
continues
caused
to
by
grow taller
if
too.
it's not caused by the earthquake, then what would it be caused by?
What's not caused by the earthquake?
So it shrunk 2 feet.
2 feet?
Yeah, in 1934.
But almost 2 feet. But then they realized that when they collected data that wasn't the earthquake wasn't the reason why it shrunk. Yeah.
Wait, what?
Yeah.
Okay.
Oh yeah, wait. Okay, so the last major earthquake near Mount Everest in 34, the mountain shrunk by 63 centimeters.
And then later in this
They were curious if the earthquake had done this.
And then this paragraph it says, after gathering data from sensors, the scientists determined that Mount Everest did not change height due to the massive 7.8 magnitude. We will continue.
Okay, so wait. So the earthquake does make some changes, but the earthquake did not make the changes that transpired then.
Yeah. It's a little confusing.
I was gonna say that it grows like about it. Mount Everest keeps growing each year.
Say more.
Like I don't know how it does grow, but it just keeps growing. And after the earthquake, the mountain shrunk by 63 centimeters, almost 2 feet.
Yeah, I was talking with Maya Taylor about that. That was back in the 1934 earthquake, right?
Yeah.
Right, but you said it gets taller each year? What does that mean?
It just grows.
It grows. Interesting, and then you said what?
And then, like, after the last major earthquake, it shrunk.
Yeah, but then you said a question. You were like, I don't know what.
How it grows?
Yeah, isn't that odd? Wait, so mountain grows taller, right? At the same time, the mountain moves towards Dex, and then at the same time during this event, it did what? It went what? Talk to me. Move back, right? Okay, cool. Anything else you guys found from the reading or anything like that? I've heard from these people, so I'd love to be somebody I haven't heard from. Joey?
I put in my wonder what causes Mount Everest to move.
Oh, cool. Okay, great. So do we want to just jump to the wonders? Well, cool. You said what causes Mount Everest to move? Excellent. What else were we wondering about? Max?
What causes it to shrink too?
Yeah, like weird. It moves, it shrinks. Dex?
Why did it go southwest?
Why did it go southwest, right? When it was like perfectly happy going northeast, right? Not that it's happy, but you know what I mean. Go ahead, Miles.
So if we're still like alive as humans, in a billion years, if it keeps on growing, would it get like to the height of the moon?
I don't know. That is a really interesting question.
Interesting.
Margaret?
Isn't the tallest mountain in the world actually an underwater volcano?
So what?
So, like,
How does this relate? I'm confused.
because it says that Everest is the tallest mountain in the world, but I've read at Queens and other places, I've read that the tallest mountain in the world is actually an underwater volcano by Hawaii.
Does anybody have a question about what Margaret just said? Because I thought this was all about Everest.
Yes.
Tiff?
Is a volcano a mountain?
Great. I don't know. That's a great wonder. Did you write it down? Olivia?
Well, I mean, I think we're talking about above sea level, but it's under sea level. It doesn't really talk about on the earth. Like, still on the earth, like, but it's still on plates.
What are those?
Like, tunnel plates are the things that cause earthquakes and volcanoes.
So let me just make sure I heard this right. Olivia, you're saying this has nothing to do, like what Margaret's bringing up is below sea level, but Everest is above sea level. So when it's above sea level, it's a mountain. When it's below sea level, it's a, what? A volcano? Okay. I don't know. Yeah, I'm just as confused as you are.
The first indicator on the instructional walkthrough tool asks if the lesson is grounded in supporting students' understanding of a phenomenon. As we saw in this video, this is a strong example of a teacher grounding science instruction in a phenomenon. Students weren't just told about the earthquake on Mount Everest, but they were able to experience it through the video and the artifacts. They were also asked to try to make sense of it based on their prior knowledge by recording and sharing their initial ideas and questions. Next, let's consider the second question of high-quality scientific content. Does the lesson focus on the development and use of grade appropriate elements of the science and engineering practices, disciplinary core ideas, and cross-cutting concepts? Let's start with the science and engineering practices, which we briefly introduced during the previous session. In this lesson, we saw that students had opportunities to work with two science and engineering practices. Students had the opportunity to ask questions of one another and to engage in argument from evidence based on what they found in the video and in the articles. The progression of science and engineering practices can also be used to determine if students are working with the practices at a grade appropriate level. This progression is found within the Tennessee Science Standards. The matrix you see on the screen can be found on page 27 of the Tennessee Science Standards, which has been included in your resource folder. These progressions help us to understand what each practice looks like at a grade-appropriate level. Let's take a look at what asking questions looks like in 6th through 8th grade. At this grade level, questions should originate based on students' experiences, as well as the need to clarify and test other explanations. Questions should also lead to explicit relationships between variables. In the video we watched, we heard students ask questions based on their experiences and what they saw in the video and news reports. And we heard them questioning the relationship between the earthquake and the height of the mountain, while considering how the height of the mountain had changed over time. For this reason, this is a grade-appropriate way for students to engage with this science and engineering practice. Now let's take a look at the disciplinary core ideas. In this lesson, students are working toward an understanding of Earth's systems. Just like for grade-appropriate assignments in Session 2, we can use Appendix E to help us understand the disciplinary core ideas at this grade band. This lesson aligned with the disciplinary core idea ESS2B, which means Earth and Space Science, Earth's System, number 2, and Plate Tectonics, letter B. If we look closely, we can see that the core idea here is that plate tectonics is the unifying theory that explains movements of rocks at Earth's surface. We can see that the exploration of today's phenomenon in the video is preparing students to explain the increase or decrease of the mountain size based on the theory of plate tectonics. Finally, let's examine the cross-cutting concepts. In this lesson, students are working towards the unifying idea of cause and effect. On this first day of the unit, students are not yet naming the cause, but they are identifying the effects, which is the change in the mountain size, and they are hypothesizing about the cause. This progression of cross-cutting concepts can be used to determine if students are working with the concepts at a grade-appropriate level. This progression is linked within the Tennessee Science Standards and can be found on page 22 of the Tennessee Science Standards reference guide that's been included in your resource folder. These progressions help us to understand what each concept looks like at a grade-appropriate level. For cause and effect at this grade band, students should be connecting their explanations to specific scientific theory and use those relationships to make predictions. In the video we watched, we heard students identifying the effects and wondering about the causes. Since this is the first day of the unit, students are not yet demonstrating this cross-cutting concept at the full demand of the grade band. They do, however, have an opportunity to interact with this cross-cutting concept with their use of the science and engineering practices and the core ideas. Because students had an opportunity to experience and work with a phenomenon, and we saw evidence of the integration of the science and engineering practices, cross-cutting concepts, and disciplinary core ideas, this video is a strong example of high-quality scientific content and would receive a score of yes. After considering high-quality content, we look to see if the teacher's instructional practices support all students in learning the content at the depth intended by the standards. Pause the video here to read through the indicators of high-quality instructional practices. After you've read through the instructional practices, resume the video. The instructional practices listed in the Science Walkthrough tool are research-based teacher actions that support students in making sense of the science. One of those instructional practices is that the teacher leverages students' prior knowledge and experience. On the slide here, you can see an example of a chart that this teacher created later in the lesson to gather students' ideas of other phenomena that might be related to what they had read about Mount Everest. By intentionally connecting to relevant and prior experiences, the teacher helps students to understand knowledge in context and internalize its interconnectedness, which is essential in developing scientific literacy. In addition to leveraging students' prior knowledge and experience, teachers can also support sense-making by doing these things: using multiple explanations, representations, models, and/or examples, deliberately checking for understanding and making necessary adaptations, and summarizing the learning throughout the lesson to reinforce its focus. The last component of rigorous science instruction is student ownership. For student ownership, we look to see if students are responsible for doing the scientific thinking in the classroom. For student ownership, we look to see if students are expressing their ideas, that they talk about and ask questions about each other's thinking, that they are sharing their thinking as it develops and revising it as their understanding deepens, and that they are using scientific language as appropriate to the content in their written explanations and discussions. We've had a chance to walk through an example of high-quality instruction using the 8th grade plate tectonics video. Now let's practice using this tool to consider instructional practices and student ownership for a high school physics lesson. As you watch, consider the indicators of the instructional practices and student ownership. As you watch this video, jot down thoughts and evidence and questions about this teacher's use of instructional practices and the ways in which you see students taking ownership.
As you wrap it up in the next 10 to 20 seconds, finish writing what you're writing. Now here's what I'd like you to do. This part of the lesson is going to be observation. That means I want you to look at the demonstration. You can get out of your seats. At this time, I don't want you writing. I'm going to give you plenty of time to write about it, but first I want you to see it. I want you to come up here in a position where you can see the demonstration so you can get out of your seat if you need to. And I have 2 beakers. I have one beaker right here with a thermometer in it that reads 80 degrees Celsius. And I have another beaker right here with a thermometer in it that reads 21 degrees Celsius. So just to be clear, I have one that reads 80 degrees C and one that reads 21 degrees C. So I'll call this T sub H and I'll call this T sub C. Of course, T sub H stands for the hot and T sub C stands for the cold. Both of these are water, and I would like you to observe what happens. I have some red dye. I'm going to drop it in there, and I want you to observe what's going to happen. I'm going to tell you what I'm not going to do. I'm not going to stir it. So just watch for a moment. As you're watching it, you can turn to the people in your group and just make observations. You can say anything you want. Just watch what happens.
Moving way faster. Hold on. Some sort of that one oh, you know what? I get it. Because the atoms are moving so much, it's kind of stirring itself. It's like
what do you mean by stirring itself?
Not stirring itself, but the atoms they're moving so much that it spreads it faster. Okay, than this one.
All right. All right. What do you notice happening here? What do you notice happening here? Go ahead.
The dye dispersed faster in the hotter water than it did in the cooler.
Okay. So what?
That's just the difference. The difference is that the hotter the molecules get, the faster that they move around in the beaker. So if you put...
Which molecules?
The water molecules.
Can you see any molecules in there?
Well, no, but, you understand that because when you put the dye in, it shows how they're moving around the beaker.
What's he talking about, Melanie?
He's talking about that when you put another substance in another liquid substance in a water, the atoms are moving faster. So in this case, when it's hotter, that they're going to diffuse faster because the atoms are moving faster than the atoms that are in the cold.
Can you see any atoms in there?
No.
Then why are you so sure that atoms are going on?
Because of atomic theory.
Tell me more.
Atomic theory says that everything's made up of matter and atoms in it.
Okay, I want to be kind of clear. That's correct. Here we're actually talking about molecules. Which molecules in particular? water, hydrogen and oxygen atoms that come together to make water molecules. And we can't see those. We can't see them at all. If I look in there, it looks like liquid to me. If I try to see particles, I simply can't see them. But the dye helps us to infer something. And it's helping provide evidence for the model, the atomic model that you're talking about. And I would like you to take a moment right now to sit down in your groups and discuss what kind of evidence did this observation give you about the atomic model or the molecular model and temperature. So sit down for a moment and give that a discussion.
The way I saw it, like you can picture it, like just imagine there's like a bunch of tiny little balls in the water. And since when it's hotter, they're moving a lot faster. So imagine just dropping something into all that, you see the balls just moving the liquid, the other liquids that were dropped in there around faster than this one. Here they just fall and they can just move throughout and they won't diffuse. They won't diffuse as fast as water temperature.
Okay guys, let me be clear. This is a talking time, not a writing time. I'm going to ask you to write in a moment, but first I want you to talk. So the question is...
Pause the video here and take 3 minutes to compare your notes about teacher instructional practices and student ownership to the indicators in the instructional walkthrough tool. After you finish comparing your notes to the indicators of the walkthrough tool, click to resume the video. Let's talk about what you noticed regarding the instructional practices and student ownership in this video. What evidence did you see of high-quality instructional practices? In the video, we saw the teacher make the concepts explicit by drawing a model on the board and using the demonstration of atomic theory with the 2 beakers. In this short snippet, we didn't see the teacher using all of these practices, but what we saw was a strong demonstration of the indicators here in this section of the tool. What evidence did you see of student ownership? We saw that students immediately jumped in to share their ideas with a partner once the discussion began. We also heard reference that students were going to be given the opportunity to write after they had discussed. Students spent significant time building off of one another's ideas, and students used scientific language like atomic theory and energy in their explanations. For these reasons, this video is a strong example of instructional practices and student ownership. Now that we've explored the walkthrough tool, let's reflect on our learning from this session. If we want to prepare students for the future, we need to think about how we develop true scientific literacy beyond just the memorization of facts. STEM careers require the ability to think critically and make use of scientific knowledge. If we only focus on the retention of information, we underdevelop students' abilities to do science and to engage in scientific thinking, which has huge implications for the future and how our students become productive and active citizens. Think about everything that you've learned in Session 2 and Session 3, along with any instructional priorities that you already have. What would your vision of instructional excellence in science look like now? Pause the video here to jot down some notes on these questions. How does strong science instruction prepare students for the future? What does your vision of instructional excellence in science include? Take 3 minutes to jot down some answers to these questions. After you've reflected, resume the video. We invite you to share these responses with your colleagues who are also participating in STEM.LD to continue your learning and to identify opportunities to improve science teaching in your classroom and in your school. This concludes our STEM.LD orientation trainings focused on science education. We invite you to engage in the other 2 STEM learning tracks focused on math and CTE as is relevant for your role. Before moving ahead, please take a minute to complete the attendance survey using the QR code or web address shown on the screen. Once you've completed the survey, you will receive a confirmation email to confirm your completion of this session. In addition, I've included my email address, Elizabeth j.nagley@tntp.org here for your reference. Please feel free to reach out via email with questions about the content of this training. Thank you for completing the STEM.LD orientation training. We hope that this has been a valuable introductory learning experience for you, and we look forward to engaging with you as you continue in the STEM.LD partnership.